Bismillahirrahmanirrahim. This is our third lecture, and in this lecture we will study about the complex exponential signals. In previous lecture we studied about the complex number and the basics of complex exponential signal. In this lecture we will study about the different type of the complex exponential signals. Any signal written in exponent form can be named as exponential signal. Generally we write the exponential signal as x of t equal to c e power a t. Where c is a number, a is a number, and depending on the nature and the value of this c and a, the complex exponential signal behavior does change. So based on the value of the c and a, we will name these signal whether real exponential or the complex exponential. So depending on the values of c and a, the complex exponential signal exhibits several different characteristics. First of all, we will study the real exponential signal. General form of the exponential signal is discussed above is x of t equal to c e power a t. When c and a can be any number like 5, 3, 2, any like this number. When c and a both are real, we call the exponential signal as real exponential signal. For example, x of t equal to 2 e to the power 5t. So this is a real exponential signal where c is equal to 2 and a equal to 5. So in real exponential, these c and a both are real. Now suppose c is equal to 1. C is 1, c can be any value, can be 5, 3, 2, can be any real number, but for simplicity we suppose that c is equal to 1 and a is greater than 0. A is greater than 0, like a is equal to, can be 1.5, 2, can be any positive value. C is any a is any positive value. Now for this supposition, when a is greater than 0 and c is equal to 1, x of t, if I plot x of t, so x of t can be plotted like this: at t is equal to 0, e power a, and t is equal to 0, so e power 0, the x of t is 1. As the t increases, here the t values of t increases, here the t value decreases. So as the t value increases, x of t will be increasing exponentially, and as the t value decreases, the x of t will be decreases exponentially. So a signal, real signal of this type, when a is greater than 0 or a is any positive number, 0.25, 0.5, 0.3, 5, 30,000, can be any positive value, then as the t increases, value of x of t increases, it is called as growing exponential. See over here, the x of t value is increasing. And in second case, if a is negative, that is a value is less than 0, now with increasing t, as the value of the t increases, its x of t will be decreasing. So for negative values of t, the x of t will be having higher values, and for positive t, as the t increases it will be decreasing. So we call this type of signal as decaying exponential and this type of signal as growing exponential. Think over it and just change. For example, take a is equal to, for example, 2, and plot x of t for different value for 0 and t increasing. Plot this signal x of t and you will have this like of behavior. Next we have periodic complex exponential and sinusoidal signal. Periodic complex exponential and sinusoidal signal. In the when the value of a is purely imaginary, we call that signal as periodic complex exponential signal. When a is purely imaginary, when the value of a is purely imaginary, we studied in the previous class that the complex number has two part. For example, z is a complex number, it will be having two part, 2 plus, for example, j3. So this is the real part of the complex number, this is the imaginary part of the complex number. Now if z is equal to j3, it means that this number is purely imaginary, its real part is 0. And if z is equal to 2, it is a real number, purely real number, because its imaginary part is 0. Its imaginary part is 0. So in periodic complex exponential signal, the a must be purely imaginary and c is real. Suppose c is real and equal to 1. So the we will be having x of t equal to e power j omega naught t, means that a is equal to j omega naught, purely imaginary number. Now x of t equal to e power j omega naught t. Now this signal, when the value of a is purely imaginary, this signal is having a very important property, and that is that this signal is periodic. This signal must be always periodic. This complex exponential signal must be always periodic. When the a is purely imaginary, that complex exponential signal must be periodic, and we have verified this in the previous lecture. See once again over here. For periodic signal, we studied that it does repeat itself after some regular interval, or the shift of if it is shifted of one time period shift is brought, the signal remains unchanged. So e power j omega naught t must be equal to e power j omega naught t plus t. So e power j omega naught t, we can write this as this, and to be periodic, this e power j omega naught capital T must be equal to 1, and this is equal to 1 when omega naught t is equal to 0 or 2 pi. So the time period will be equal to t equal to 2 pi by omega naught t. Now another signal which is very closely related to the periodic complex exponential signal is a sinusoidal signal. We the sine or cosine, we call this signal as sinusoidal signal. So these signal are very closely related to the periodic complex exponential signal. For example, our signal x of t is equal to a cos omega naught t plus phi. Now a is the amplitude, omega naught is frequency, and phi is the phase of this signal. Now this sinusoidal, this is a sinusoidal signal. This sinusoidal signal can be written in terms of complex exponential signals. This signal can be written in terms of complex exponential signal is a cos omega naught t plus 5 is equal to a e power j omega naught t plus 5 plus e power minus j omega naught t plus 5. Do remember, I think you remember, you know that cos theta is equal to e power j theta plus e power minus j theta divided by 2. Is it clear? So here we have used that relation. So a e power j phi e power j omega naught t divided by 2 plus e power a e power minus j phi e into e power minus j omega naught t divided by 2. Similarly, the complex exponential signal can be written in terms of sinusoidal signal. For example, e power j omega naught t plus phi, this is equal to cos omega naught t plus phi, Euler formula. You have studied it in the previous class, Euler formula, that e power j omega naught t plus phi equal to cos omega naught t plus phi and j sin omega naught t plus phi. This is the real part and this is the imaginary part. Now if I write real of e power j omega naught t plus phi, I mean that the real part of this signal, and the real part of this signal is cos omega naught t plus phi. So it will be equal to cos omega naught t plus phi. And if I write imaginary of e power j omega naught t plus phi, I means that the imaginary part of this signal, and the imaginary part of this signal is sin omega naught t plus phi, and here it is. So whenever I write real e power j theta, what does it mean? That the real part of this signal, and the real part of this signal is equal to cos theta. Okay. Now let us take an example. Suppose x of t equal to 3 e power minus j pi by 2t. It is being multiplied within, this is a complex exponential signal and this is a complex number e power j pi. The complex signal is multiplied with a complex number. So the exponent must be added. So 3 e power j minus pi by 2t plus pi. And here we have another signal y of t. Y of t is equal to 3 e power minus j pi by 2t and 3 e power minus j pi by 2t. Now if you see, these signal looks similar, only the difference is that in x of t we have, here we are having another a constant added, that is pi. This is nothing but the initial phase. This is the initial phase. Its phase is different than y of t. Now if I find the omega is equal to minus pi by 2. Now find the time period is equal to 2 pi by omega, and the magnitude of the omega, absolute value of omega. So 2 pi by 2 equal to 4 seconds. It means that this signal will repeat after 4 seconds, or will complete one cycle in 4 seconds. Here for y of t, if we see omega is equal to minus pi by 2 and time period is equal to 2 pi by absolute value of omega, so 2 pi by 2 So here again the time period is 4 seconds. What does it mean? It means that this signal will also complete this rotation in 4 seconds. Now the frequency of this signal, to find the frequency of x of t, f is equal to 1 over t, and t we have find it that it is 4, so 1 over 4 equal to 0.25 hertz. And for y of t, f is equal to 1 over t. Here again the time period is 4, so frequency will be 0.25 hertz. So we can conclude that their time period and frequency is same, only starting phase is different. Only starting phase is different. Now let us plot x of t and y of t on real imaginary plane. So x of t in real imaginary plane, so x of t we know that is equal to 3 e power j minus pi by 2 t plus pi. So at t is equal to 0, when time is equal to 0, so x of 0 is equal to 3 e power j minus pi by instead of t we are calculating the values of the signal specifically at t is equal to 0. So here instead of t we will be having 0 plus pi, so 3 e power j pi, so 3 e power j pi. So here if you see, magnitude is equal to 3 and theta is equal to pi, so at t equal to 0, x of t is having amplitude of 3 and angle of pi. So we can plot it like this: m is equal to 3 and theta equal to pi. So this is 3 amplitude and this angle is pi. This is the plot of x of t. Now as the t increases, it will start rotating from here, and in 4 seconds it will complete its rotation. Now let us plot y of t. So y of t in real imaginary plane, y of t equal to 3 e power minus j pi by 2 t. At t equal to 0, y of 0 equal to 3 e power minus j pi by 2, and instead of t we are finding the value of y of t specifically at t is equal to 0, so we will be having 0 instead of t. So 3 e power 0 equal to 3. Now you see that magnitude is equal to 3 and theta is equal to 0. So in real imaginary plane this signal will be plotted as a magnitude is equal to 3 and angle is equal to 0. So this signal will start rotating from here. This is the difference between these two signals. Their frequency and time period is same, only the difference between the two is their starting phase. Now let us plot these two signal in suppose x of t equal to cos omega t. So this is the plot of the cos omega t, this is the plot of the x of t, this is the and y of t equal to cos omega t plus pi by 4. So this y of t and x of t are same, both are cos, but y of t is same as x of t but is advanced by pi by 4. So when a signal is advanced, we know that it is shifted to the left. So this y of t is nothing but x of t shifted to the left. by pi by 4. So this signal, this is the plot of the y of t, that here if you see 1 is 1 appears when t is equal to 0, but here 1 appears somewhere over here. So think over it. It is very simple but very important. This is we call this the pi s phase. Here the phase, starting phase is pi by 4. So this is all about the phase and complex exponential signal. Now till now we have studied the two types of complex exponential signal, when C and A both are real, when A is purely imaginary. Here in this case, in general complex exponential signal, it can be expressed in terms of two cases we have examined so far. Here in this case, we will be taking C as a complex number having a real, both real and imaginary part, and A will also be a complex number having both real and imaginary part. So here we have written that C is complex number expressed in polar form. The polar form of the complex number is here the m magnitude and the theta, and A is the complex number expressed in rectangular form. In rectangular form we express the complex number as the real part plus the imaginary part, 2 plus j3. This is the for example 2 plus j3, this is the rectangular form of the complex number. Now C is equal to magnitude of C e power j theta, where this is the magnitude of C and we can express it as m. So C is equal to m e power j theta, and A is equal to r plus j omega naught. R is any number, omega naught is also any number. So x of t can be written as, this is C value m e power j theta and e power r plus j omega naught t. So arranging the terms, m e power j theta into e power rt into e power j omega naught t, rearranging the terms, so x of t will be equal to m into e power rt e power j omega naught t plus theta. So if you see over here, m is magnitude, can be any number, e power rt, this is the real exponential signal studied at today. We studied it in the very first slide. So r is any real number. E power j omega naught t, this is the complex exponential signal. Complex exponential having some initial phase theta, So suppose we A is equal to 3 plus j2 and C is equal to 1 e power j pi by 2. So x of t will be equal to C e power at. C is e power j pi by 2 into e power 3 plus j2 t. So x of t equal to e power 3t e power j 2t plus pi by 2. So this is the real exponential, and as we know that A is greater than 0, so this is a growing exponential. And here we are seeing that the A is purely imaginary, so this is the periodic complex exponential with initial phase of pi by 2. So at t is equal to 0, x of t will be equal, x of 0 will be equal to e power 30 into e power j 20 plus pi by 2 1 e power j pi by 2. So this signal x of t will be plotted like this. at t is equal to 0, it will be, the phasor will be here, and its magnitude will be 1. This is pi by 2 angle. As the t increases, this exponential will start rotating, and with rotating, its amplitude or magnitude will be also increasing, because it is being multiplied with the e power rt, e power 3t. So its amplitude will be increasing and the phasor will be rotating like this. So here you can see that now as t increases, e power 3t, this is being multiplied, this real exponential is being multiplied with this periodic complex exponential signal. So this e power 3t will increase, which will increase the magnitude of the phasor. So with increasing t, phasor will keep rotating and increasing. Here the previous slide is continued. So x of t equal to e power 3t e power j 2t plus pi by 2. Now if I write this in rectangular form, in real imaginary form, so x of t equal to e power 3t multiplied by cos 2t plus pi by 2. If you remember, we studied that e power j theta equal to cos theta plus j sin theta. Here instead of theta we are having 2t plus pi by 2. That is why we can write this as equal to cos 2t plus pi by 2 plus j sin 2t plus pi by 2. Now e power 3t cos 2t plus pi by 2 plus e power 3t j sin 2t plus pi by 2. Now if I write real of x of t, so real of x of t means that the real part of the x of t, and the real part of the x of t is this e power 3t into cos 2t plus pi by 2, and this is nothing but the growing exponential e power 3t is multiplied with a sinusoidal signal cos 2t plus pi by 2, which is having an initial phase of pi by 2. So this is this signal, that this signal is like this. As the t increases, the cos signal does increases like this. And if you see, this is the exponential being multiplied with the sinusoidal signal. And if I plot the imaginary x of t, so imaginary of x of t is nothing but the growing exponential being multiplied with the sinusoidal signal sin 2t plus pi by 2. So this is the nothing but the sine signal shifted by pi by 2. So sin t is equal to 0, it will be 1 and can be plotted like this. Initially it is 0, and as the t increases it is going to increase like this. Is plotted over. Think over it and you will learn what is meant by this. Now this was all about the continuous time complex exponential signal. Now let us see a quick view of the discrete time complex exponential signal. We have studied in the very first lectures that the difference between the discrete time and complex exponential signal is that the discrete time signal and continuous time signal, that the independent variable in the discrete time is discrete, that is not continuous, And in case of the continuous time signal, the independent variable that must be continuous, that must be from a continuum of values. And in discrete time it must be discrete time signal, the continuous variable must be discrete instants. So the general form of the discrete time complex exponential signal is x of n equal to c alpha power n, or x of n equal to c e power beta n, where alpha is equal to e power beta. So real first first type of the discrete time complex exponential signal is real exponential signal. And real exponential signal are those signal where c and alpha are both are real. So based on the values of the c and alpha, the signal will exhibit different properties. For example, see the a. If alpha is greater than 1, alpha is greater than 1 mean 2, 3, 4, 5 can be any value, 2.5, 3.5 can any value greater than 1. So you can see that the magnitude of the x of n will grow exponentially like this. Suppose here I have solved, suppose alpha is equal to 2 and c is equal to 1. So x of n will be equal to c alpha n and is equal to 1 2 power n, where n can be any integer, 0 plus minus 1 plus minus 2 plus minus 3 and so on. So for example, we are finding the value of x of n at minus 3. So x of minus 3 will be equal to 2 power minus 3. So if I make 1 over 2, so 3 will become positive, 1 over 2 is 0.5. So 0.5 power 3 is equal to 0.125. X of minus 2, so 2 power minus 2, 1 over 2, 0.5 power 2 equal to 0.25. X of minus 1, so 2 power minus 1, so if I make 2 is 1 over 2, so the minus 1 will become positive and 1 over 2 is 0.5, so 0.5 power 1 is equal to 0.5. You can see that the x of n is going increasing. X of 0 is equal to 1 and x of 1 equal to 2, x of 2 equal to 4, x of 3 equal to 8 and so on. So if I plot the values of x of n across the different values of n, so we will be having this plot, and this is a growing exponential. Now suppose if the values of the alpha is greater than 0 and less than 1, if the value of the alpha is greater than 0 and less than 1, that is 0.5, 0.25, 0.3, 0.7, 0.8, 0.9, 0.9, 0.25 like this, 0.95, so it will be decaying exponential. Now if the alpha is greater than minus 1 and less than 0, that is alpha is negative, so magnitude keep on alternating and decaying. The magnitude of the alpha will be positive for the some values and will be negative for some values, then positive, then negative, and will keep on decaying. And if alpha is less than 1, so the x of n will be alternating and growing. Think over it and plot it by yourself in your notebook, taking different values of alpha according to these types. Now the sinusoidal discrete time sinusoidal signal. Suppose x of n equal to c e power beta n, where beta is purely imaginary, that is beta is equal to j omega naught. So x of n equal to c e power j omega naught n. Suppose c is equal to 1, so x of n will be equal to e power j omega naught n. Same is in continuous time signal, e power j omega naught will be equal to cos omega naught n plus j sin omega naught n. However, in case of continuous time, we studied that e power j omega naught t is periodic for any value of omega naught. We studied that e power j omega naught t, this must be periodic. This is periodic. This signal has a property that this is periodic for any value of omega naught. However, in case of discrete time signal e power j omega naught n, this signal is almost similar to this continuous time. The only difference is the independent variable. Here we are having t and here we are having n. But there is a big difference that this signal e power j omega naught n, this is not always periodic. Sometime it will be periodic, sometime it will not, depending on the value of omega naught. So next we are going to study the periodicity property of discrete time complex exponential signal. Consider, before going to define how to find that whether a specific discrete time signal is periodic or not, let us see one important note, that consider e power j omega naught plus 2 pi. See this complex exponential signal, this is equal to e power j omega naught n and e power j 2 pi n. This is equal to e power j omega naught n. Why? Because e power j 2 pi n equal to cos 2 pi n plus j sin 2 pi n, where cos 2 pi n is equal to n for all values of n, as n is integer. Cos 2 pi is equal to 1, cos 4 pi is equal to 1, cos minus 4 pi is equal to 1, and so on. For any value of n, this cos 2 pi n will be equal to 1 and sin 2 pi n is equal to 0. So e power j omega naught plus 2 pi n is equal to e power j omega naught. What? So we can conclude that we have same exponential at omega naught plus 2 pi is same as at omega naught. This is something I have written visa. I think I need to write the visa. So if you remove this and see that exponential at t is t, omega naught plus 2 pi is same as at omega naught, mean to say that the exponential at omega naught is same at omega plus 2 pi, omega plus 4 pi, and omega naught plus n pi. Sorry, 2 pi n. 2 pi n, any multiple of 2 pi. So in discrete time, signal with frequency omega naught is identical to signal with frequency omega naught plus 2 pi, omega naught plus 4 pi, omega naught plus 6 pi, and so on. So okay, this was 7, this is 8. So in order for signal e j omega naught to be periodic, we must have periodic with n greater than n, we must have e power j omega naught equal to e power j omega naught n plus n. So e power j omega naught n is equal to e power j omega naught n into e power j omega naught n, where capital N is the period. And capital N is period. So we have studied that periodic signal is a signal if a shift of one time period is brought, it remains the same. So here we have actually brought a time shift of n, and n is the period. So if this signal is periodic, this e power j omega naught n must be equal to 1. So e power j omega naught n equal to 1. Omega naught n must be a multiple of 2 pi. Then e power j omega naught will be equal to 1. So we can say that e power j omega naught n equal to 2 pi m any integer. M can be any integer, or omega naught divided by 2 pi is equal to m by n. So e power j omega naught n will be only periodic if omega naught divided by 2 pi is a rational number. If not, then will not be periodic. So it is a very important property to check whether the discrete time complex exponential signal or discrete time sinusoidal signal is periodic or not. See that if its omega naught divided by 2 pi results in a rational number, then this signal is a periodic signal. And if this omega naught divided by 2 pi results in an irrational number, this signal is not periodic. And what is rational number? Rational number are those number which can be written in the form of p by q, and irrational number cannot be written in the p by q form. Pi is a irrational number, I think e is a irrational number, and see the definition of the irrational number. What are the we have only few irrational numbers. So fundamental period will be equal to n equal to m 2 pi by omega naught. This is an example. Find whether the given signal is periodic or not, and also find its fundamental period. For example, x of n equal to sine 6 pi by 7n plus 1. So omega naught is equal to 6 pi by 7. This is omega naught. This is equal to 6 pi by 7. This is its omega naught. So omega naught must n equal to 2 pi by m. 2 pi m. Omega naught divided by 2 pi must be rational. So here omega naught is 6 pi by 7. So 6 pi by 7 divided by 2 pi. So pi cancel, 2 and 6 cancel, result in 3. So 3 by 7 is a rational number. So this signal is periodic. Fundamental period n is equal to m 2 pi by omega naught. So so n is equal to m into 7 by 3. The value of m must be taken such that n result in some whole number like this. So to have the n equal to 7, m must be taken as equal to 3. So take m is equal to 3 and n will be 7. So its fundamental period is 7. Another example is given that x of n equal to cos n by 6. Check whether periodic or not. Find fundamental period if periodic. So here omega naught is equal to 1 over 6. So omega naught divided by 2 pi is equal to 1 over 6 into 2 pi, 1 over 12 pi. So 1 over 12 pi is a irrational number. So not periodic, because pi is a irrational number. So this signal is not periodic or aperiodic. So the fundamental period doesn't exist. Let us have a quick comparison of the e power j omega naught t, the periodic complex exponential signal, continuous time complex exponential signal, and this e power j omega naught and discrete time complex exponential signal. Despite of the two signal being very similar, there are is a big difference between the two complex exponential signal. If you see e power j omega naught t, distinct signal for distinct values of omega naught. For example, as the value of the omega naught increases, the oscillation of e power j omega naught t increases. Means that omega naught increases, its frequency increases, or the oscillation increases. However, in case of e power j omega naught n, identical signal for values of omega naught separated by multiples of 2 pi. That is, signal with frequency omega naught is similar to signal with frequency omega naught plus 2 pi omega naught plus 4 pi, as verified in the previous slide, that e power j omega naught plus 2 pi n, this is equal to e power j omega naught n. So this signal omega naught is separated by 2 pi, so these signal are identical. However, e power j omega naught t, this is a different signal, and e power j omega naught plus 2 pi t, this is a different signal. These two are different signal. However, in case of discrete time signal, when this t is n, these two are similar signal. And the second difference is that e power j omega naught t is periodic for any value of omega naught. However, e power j omega naught n, this discrete time complex exponential, is periodic only if omega naught is equal to 2 pi by n into m. For some integers n is greater than 0 and m, that is omega naught divided by 2 pi is a rational number, as proved in the previous slide. The fundamental period of e power j omega naught t is equal to undefined if omega naught is equal to 0, and if omega naught not equal to 0, t naught is equal to 2 pi by omega naught. However, in case of the e power j omega naught n, fundamental period is undefined if omega naught is equal to 0, and the fundamental period is equal to m into 2 pi by omega naught when omega naught is not equal to 0. Similarly, the fundamental frequency of the e power j omega naught is omega naught, and the fundamental frequency of the e power j omega naught n is omega naught divided by m. This is the brief comparison of e power j omega naught t and e power j omega naught n. Here again an example given: x of n equal to e power j 2 pi by 3n plus e power j 3 pi by 4n. Here this signal has two complex exponential signal. This signal x of n has two complex exponential signal, and we are asked to find the fundamental period n naught of the x of n. So, to find the fundamental period of this signal, we will first find the fundamental period of this one exponential, and then we will find the fundamental period of this exponential signal. We name the fundamental period of this exponential signal as n1, and the fundamental period of this signal as complex exponential signal as n2. So e power j 2 pi by 3 n, its omega naught is equal to 2 pi by 3, so omega naught n equal to 2 pi by m, and 1 equal to 2 pi by omega naught. n1 is equal to 2 pi by uh, 2 pi by 3 into m, so n1 is equal to 3. And for the second exponential signal e power j 3 pi by 4n, its omega naught is 3 pi by 4, and 2 will be equal to 2 pi by omega naught, and n2 will be equal to 8 by 3. Here take m is equal to 3, so n2 will be 8. Now if there are more if there are more than one exponential in a signal, fundamental period is the LCM, the least common multiple of their individual fundamental periods. Like here, n1 is 3 and n2 is 8. So 24 is the LCM of 3 and 8. So the fundamental period of this signal is 24. This is all about the today lecture. So see you in the next class. Thank you.